You're listening to Let's Talk AI.
Welcome to Let's Talk AI. Today's guest is Zhao Pan. Zhao Pan is an assistant professor in the Department of Mechanical and Mechatronics Engineering here at the University of Waterloo. Zhao, thanks for joining us today.
Thanks for the invitation, and it's my pleasure.
Awesome. So, Zhao, typically we start off with tell us a bit more about Zhao. How did this all start for you on the AI space? More importantly, where did you start your studies and how did you end up at University of Waterloo?
It will be a long story, but I will try to make it short. So I did my undergrad all in China, but my major was automotive engineering. It's very specific. Essentially, it's like mechatronics engineering, but we focus on cars a lot. So, but after that, I find cars is not that interesting. Although back then at that time, my research was about autonomous driving. And back then it was not that hot a research topic and not that hot in the industry. Um, I have a mixed feeling about it, but then anyway, I move on, and then I did my master's in Louisiana, United States. So there, I tried material research and absolutely hate it. Sorry if anybody in the audience is materials lovers, but it's a very personal preference. And then I tried solar energy. Didn't like it either. But the good thing is that I find I like physics and fluid mechanics a lot more. Then I did my PhD in Utah on the general topic of fundamental physics of fluid mechanics. I worked in a experimental lab, but my work is mainly on the data and theory side, and this is how I started following the progress in AI machine learning. Give you one example. So I have to process a lot of images when I process the experimental data, and one task is classic in machine learning, which is segmentation. Uh, I still remember it was like 2012. I took classes, and it's about computer vision. The textbook was like really thick, classic one by Gonzalez, and in that book, there's no section about AI or machine learning. And at that year, there's a thing called AlexNet coming out, and that performance is just amazing. And you don't have to know a lot to use that. So that's the amazing part of AI. And at that time, yeah, people see that this thing will take off. So by the way, AlexNet is a deep convolution neural network. So starting from there, I keep watching how it perform and see the achievement in general AI and machine learning can do, and then I start doing it by myself. So this is how I gradually, it's a long trip, but gradually end up doing AI.
Okay, so your research now is more here at University of Waterloo focused on fluids and fluids engineering and the use of AI in that space. Can you give us a bit of a deep dive of what's the why? Like, what do you hope to achieve by this research?
Um, it's a bit weird to say so that I have a focus. So my lab is called Pan Lab. Pan is my last name. It's on my passport. It's real, okay. But on the other hand, Pan is also a root word. It means everything. So if you remember, there's a company it's called Pan America. So it meaning everything, everybody. So this is partially my personal interest. So when I find something is interesting to me, then I do it. I don't really care about the topic. So in my lab, we do fundamental physics of fluid mechanics, and you may find the topic is interesting, bizarre, but kind of useless. And we want to contribute knowledge for the humanity. And we also try to do something useful. In that realm, we apply AI algorithm to some uh, um, applications, and we also try to develop new AI algorithms. So I can give you some examples. So after I moved to Canada about 3 years ago, then I started one research project. It is about how can we navigate ships in ice-covered waters. This is um, essentially it is an important problem in next 30 years or 40 years. Here's the why. Climate is getting warmer and warmer, and I hope not, but I don't believe we can really stop it fast in the near future. And Arctic Ocean will be melt. Will melt. Okay, so what? It means that the northern route, the shipping route, will be open. No more ice will cover there, and so that we can ship stuff from Asia to Europe to North America through the northern route. And the benefit of doing so is we can save up to 40% of the time, the money, fuel, and the CO2 emission just by going through the ice covered waters near Canada and near Russia. So this is a topic that particularly interested to Canadians and the Canadian government. So to achieve this, the first step is we want to build a ship that similar to Tesla that can identify the ice situation around the ship, around the vehicle. So this is one research I'm doing is I want to develop a sensor or sensing system so that the ship can know, oh, there's a large piece of water in front of the ship, and where's the ice I should avoid, and where is the water I can go, and where is that piece of ice that the ship just can't crush. After this, then we can do planning, and the ship can find its route. So yeah, essentially, I'm developing a Tesla, but it's for ships navigating in ice-covered waters. It will be used in the next 10, 20, 30 years.
Okay, wow, this is fascinating. So, I assume you're not doing all this work on your own. Do you have a small team you're working with?
Yeah, I feel I'm very lucky to be Waterloo. We have a lot of colleagues, very open-minded and have the vision. We're working together. And we also have a lot highly motivated students, undergrad students and grad students. Yeah, we're working together on this. So actually, we just got a PhD student from Ukraine, and that student will also work on this team.
Okay, that's great. That's great. So, how many in total? Sorry, roughly did you say you had?
You mean the students?
Yeah, students that are working in this area.
Oh, right now we have two PhD students, two master students, and five undergrad students working on the whole project. We just started, but hopefully, in a few years, we can have something awesome.
Okay, so you talked about recognition or avoidance of ice and ice chunks, obviously the threat to the vehicles. Is this research applicable in other areas? Is it applicable in other parts of the world? What's your thoughts about that?
That's a fantastic question. So the one thing I like AI about is um, you can think of most AI algorithm or machine learning algorithm. It's sort of like regression or fitting. So that algorithm is so applicable to almost everywhere. So once you know one algorithm well enough, and you can always find the application outside your domain. It's pretty much like when you have a hammer, everything looks like a nail. Um, and this AI and machine learning mentality, I'm not even talking about the algorithm, is a very powerful, very heavy hammer. One example is, um, so I was thinking, yeah, I'm doing data science and machine learning already for the ice navigation in ice research already, and I also doing some uh, physics of fluids research. How can I combine them together? So here's one perfect example. Um, Apparently, I think I said it. I grew up in China. So over there, how my grandma cook deep when she deep fry something, she want to know the oil temperature. How she got that information is not measure it by some thermocouple or any instrument. What she does is she dip a bamboo chopstick into the hot oil, and then she tried to watch how the bubbles coming out from the chopsticks. Watch bubble, okay? And she also tried to hear the noise made from the chopstick, hear the noise. And by those two very different information, and she can tell the oil temperature really well. And think about what's going on in this simple process. She watched the bubble. The behavior of the bubble in hot oil is a classic fluid mechanics problem. And she hear the noise. And that's another classic problem from acoustics. Arguably a subrealm of fluid mechanics. And her brain, over years, got trained to process those two very different information and got the temperature. So there must be a small portion in my grandma's brain. It works like a neural network. And to be more specific, this task is called multimodal learning. It simply means for one thing, we have different information or measurement from different sensor or sensing system, and let's train a neural network to combine everything together and output something about that system or process. So this is another research we're doing as a side project. It's fun, it's interesting, but kind of useless. But the algorithm behind it can be totally applied to so many different areas. Back to the icebreaker or navigation in ice problem. So we have LiDAR, radar, different cameras, like virtual camera and IR camera and the polarization cameras installed on the ship. They are all different eyes, and we also will install some microphones. So when the eyes hit the ship and making different noises, and hopefully with all those sensors combined with multimodal learning, and we can have some decent information about the ice and the water around the ship.
Awesome. So, how do you fund all this research?
This is a hard question. I have to think.
This is mostly like by NSERC and government agency, or is there typical like Northern Ice consortiums that are trying to solve this, or tell us more about that.
Oh yeah, you asked how I found it, not how I find.
No,
Uh,
fund.
okay. So most of the research about ice in navigation in ice covered waters is funded by NRC. So it was about 2 years ago. Then we started the conversation with NRC. It was a small project, and then later we did more research and we applied bigger funding from again NRC and Waterloo Joint Research Center. So and we're still looking for more resources so that we can upscale this research. As you can tell, it's research about a ship. That vehicle is not cheap. So we cannot afford all by ourselves. Instead, we have to rely on the partners from NRC. They have huge ice tank with model ship in it, and we have to rely on the Coast Guard of Canada when they go out and they carry our sensor suit and collect data, and then we can play with the data right here at Waterloo, which is far away from oceans.
So you haven't gone up north and ridden on one of the icebreakers yet?
No, not yet, and hopefully next year.
Okay. And okay, so I'm just going to back up for a second here. I mean, in layman's terms here, I see you're doing object recognition and avoidance, and and navigating your path. Is this work applicable to automotive? Is it applicable to maybe in a factory? Things like that. For I know there's a lot of AGVs going around factories, automatic guided vehicles, humans, things like that. Is there application of your research to those spaces?
Absolutely, yes. The ideas is always the same. If you ask, okay, what's the task, the term for the task you're dealing with right now? So the first is segmentation. So we're doing image segmentation and trying to upgrade it to video segmentation. And what do we use that for? We use it for classification. So that's the two classic tasks we're dealing with. But as you asked, uh, of course, we can apply those algorithms in other scenarios, like in the factory and for the cars running on the road. But all those things have very different requirements than the ships navigating in ice. Just give you one example. What's the difference between ships moving in water and a car moving on the road? So I have decent background in automotive engineering. I was trained. And you may think a car is not so expensive and not that high tech, but this product is especially challenging for many reasons. You don't want your car to be so expensive. It means that you cannot use any expensive sensors on it. So that's a limitation. And a car moves fast on the road and surrounding other cars. So it means the computation installed on the car must be fast. So think about those two. You want to be cheap and you want to be fast. It's hard, very hard. But back to the ship, um, I feel very lucky we find this problem. So it's a ship. It's a very expensive vehicle. In that sense, we can install a lot sensors, and we're less sensitive to the cost of the sensors. And the second, the ship never move real fast. So we can use more complex algorithms, and we can install a bigger computer on the ship. So, but yeah, back to your question. Yes, the algorithms and the frameworks can be applicable to other scenarios.
Excellent, excellent. So just looking through some of the notes here. It's incredible to see this application of you're going to do all this research on ice, but it's applicable in other market spaces and any other. Originally asked the question: is this applicable in other parts of the world, or is it only about ice? Because you talked about melting ice, and I assume that means rising ocean levels. What was above land, above water may not be above water, and hidden threats. And if you're trying to just use the visual, so does your research go subsurface? Does it go below the water and look at ice under the water or objects under the water?
That's another fantastic question. This is something we're thinking about. In the future, yes, we are going to do it, and perhaps we have to do it. So when we stick something, the sensor into the water, then that's another requirement. So out there, it's cold and it's water, and it's a requirement for the sensor to be sturdy. And another thing is when you stick your head in water and you cannot see far. So then instead you have to use something like a radar. So yeah, eventually we will use some sensor like that, but for now, no. We mainly rely on the above water sensing a system like cameras, and we also rely on a lot information from satellites. So satellites give you a large scale, really low resolution sensing. Yeah, we call it remote sensing. And on-ship sensors give you high resolution but very near range. So we also try to combine those two multi-scale sensing together for the ship to have better information. And for the you mentioned yeah, in the future the ice will be melt. I would say yeah, definitely. That's climate thing, and hard to predict, but I guess it will.
Okay. Well, thank you very much today for joining us on Let's Talk AI. We've got some more insight into yourself, your area of research, the applications, future, 40% reduction of shipping. Wow, that's a big, I'm sure all the shipping companies will love you. And we as consumers will as well. So, any last comments you'd like to add today?
Um, well, I see AI as or machine learning or neural network as a very powerful tool. It's a really good hammer. But on the other hand, the reason why it's good simply because in the past 10 years, the deep neural network stepped in. So one good side is when it's deep, performance amazingly good. But on the other hand, it turned out to be a black box. So for some research or for some applications, you don't want anything black. You want everything be transparent. So that's another research we're trying to do, and we go opposite. We go extremely shallow learning, and so that we hope.
So that's like is that is that like drawing out the logic that the AI is inferring or using behind its conclusions?
Yes. So if you look at the current deep learning algorithm, there are so many layers of neural network. And one thing we're doing in the lab right now is we want to only use just one layer of the neural network. And that thing is simple enough, and we can write down everything on paper and understand how the information goes through. And this is our constraint. We want the algorithm to be so simple, but we also want it to have guaranteed performance, so that then there's then we drive a balance. The performance is okay, and we have guaranteed convergence, and we know exactly how our algorithm would perform. So I see this is the future of the machine learning community, at least for me. It's for my research. Sometimes I want 100% transparent algorithm.
Hmm. Well, that's a great vision. Again, thank you so much today for your taking your time to share with us your vision and feedback.
Thank you.
Excellent. Okay. Well, thanks very much. Have a great day.